This is Chemistry 101, Practice Exam 3 for Spring 2020. So, my name is Mr. Dion, and let's take a look at these problems. So, question 1, which of the following statements correctly describes Boyles Law? So, you should have Boyles Law memorized and should know that Boyles Law is P1 times V1 is equal to P2 times V2. So, based off of that, we know that pressure is inversely proportional to volume. And what does that mean? That means that if pressure increases, volume is going to decrease. So if we take a look at A, the pressure of a gas is directly proportional to the Kelvin temperature. Boyles law has nothing to do with temperature, so it can't be that. In B, the pressure of a gas is inversely proportional to the volume of a gas if the temperature and the amount of gas remain constant. So that, to me, looks like the correct answer. Let's take a look at the rest of them. The volume of a gas is directly proportional to the Kelvin temperature. Again, Boyles law has nothing to do with Kelvin temperature. D, the total pressure exerted by a mixture of gases in a container is a sum of the partial pressures. That's Dalton's law, so that can't be it. And the last one, the volume of a gas is directly proportional to the number of moles of gas if the pressure and temperature remain constant. So that's Avogadro's law. So B is the correct answer. And you have to remember that when we're dealing with Boyles law, that temperature and the amount of gas are going to have to remain constant. Let's move on to number 2. Question number 2 asks, which of the following statements correctly describes Charles' law? So you should be aware of what Charles' law is, and that is volume 1 over temperature 1 is equal to volume 2 over temperature 2. So based off of this, we can see that volume and temperature are directly proportional to each other. So if we look at the first answer, the pressure of a gas is directly proportional to the Kelvin temperature. Charles' law has nothing to do with pressure. In fact, pressure and number of moles should be constant in Charles' law. The volume of a gas in B is directly proportional to the number of moles of gas. Again, we're not varying the number of moles of gas in Charles' law, so that can't be correct. In C, the total pressure exerted by a mixture of gases in a container is the sum of their partial pressures. Well, Charles' law has nothing to do with pressure because pressure is kept constant, so it can't be C. The volume of a gas in D is directly proportional to the Kelvin temperature. This would be our correct answer. And then finally, for E, the pressure of a gas is inversely proportional to the volume of a gas. That's Boyles' law. So D is the correct answer. In number 3, which of the following represent standard temperature and pressure? This is something that you should just memorize, that standard temperature and pressure are 0 degrees Celsius and 1 atmosphere. So 1 atmosphere is the pressure that's felt at sea level. But you should also remember that 0 degrees Celsius is the same thing as 273 Kelvin. So our answer is going to be B. The temperature is 273 Kelvin and the pressure is 1 atmosphere. The next question asks us, which gas under the specified conditions would come closest to exhibiting ideal gas behavior? So you can see that in the 5 answers, there's 2 gases. There's ammonia and there's hydrogen. And ammonia is a polar molecule. And if you take a look at the molecular geometry of ammonia, you can see that it's trigonal pyramidal, and overall there's a dipole. And you might remember that gases are most ideal when they're nonpolar. So if you take a look at the Lewis structure of hydrogen, which is a pretty quick one to draw, you can see that it's nonpolar. So that means there's going to be minimal attractive forces between hydrogen molecules. So that means that the best choices are going to be either A or D. Now, if we take a look at the possibilities, if A is hydrogen at high pressure and low temperature, what does that mean? If we're under high pressure, that means the molecules are going to be compressed with each other or compressed closer together, which is going to be non-ideal, because in an ideal gas, we want to have a lot of space between the particles, because that's one of the postulates of the kinetic molecular theory of gases, that gases are mostly empty space. So that means that D, where the gas is at low pressure, is going to be more ideal. Also, if you think about the kinetic molecular theory of gases, it says that gases move quickly, right? They're moving quickly and they're having inelastic collisions with the walls of the container. And that's going to occur at a higher temperature compared to a low temperature where the molecules are going to be moving more slowly. So the answer is going to be D. It's going to be a nonpolar gas, hydrogen, at low pressure and high temperature. Number 5 asks us, at 100 degrees Celsius, which gas sample exerts the greatest pressure? Well, we know that the pressure is going to be proportional to the number of particles, right? Because if you remember the ideal gas law, PV is equal to nRT. If I keep the volume and the temperature constant, and my R is obviously a constant, so you can see that pressure is going to be proportional to the number of particles. And if I take a look at all of these, you can see that A has the most particles. And that makes sense because the pressure is a result of force per unit area. Where does the force come from? The force comes from the gas particles, whether they're molecules or atoms, colliding with the walls of the container. So the more particles we have, the more collisions we can have, and therefore the greatest pressure. So in number 5, we're just looking for the situation that has the most gas particles. Number 6, 2 molecules of ethane experience what type of attractive forces? So if I was to have another molecule of ethane next door to this one, a neighboring molecule of ethane, how would they be attracted to each other? What attractive forces would they feel? So you might remember that we've looked at 3 types of intermolecular forces. So the intermolecular forces that we're concerned with are London forces, dipole forces, and hydrogen bonding. Now we know that hydrogen bonding is not a possibility in ethane because there are no oxygen-hydrogen bonds, there's no hydrogen-fluorine bonds, and there's no hydrogen-nitrogen bonds because you have to have one of those in order to have hydrogen bonding. So you either have to have an oxygen-hydrogen bond or a nitrogen-hydrogen bond, or you've got to have a fluorine hydrogen bond. So you've got to have one of those, and none of those are present. Also, there's no dipole because there are no polar bonds, because the difference in electronegativity between carbon and hydrogen is too small to be a polar bond. So the only intermolecular force that is going to be experienced between 2 molecules of ethane will be London forces. Sarin is a nerve gas that was previously used as a chemical weapon. Considering the physical properties of sarin shown in this table right here, which statement about sarin is false? So it says in A that a sample of sarin at 100 degrees Celsius exists as a gas. Well, that already seems like we have a problem here because the boiling point of sarin is 158 degrees Celsius. So what is boiling point? Boiling point is where we go from a liquid to a gas. That means that it doesn't become a gas until it reaches 158 degrees Celsius. So if the sarin gas is at 100 degrees Celsius, well, 100 degrees Celsius is less than 158 degrees Celsius. So that means a sample of sarin at 100 degrees Celsius is going to be a liquid. So this one is false. Number 8 asks us, which states of matter is most compressible? So if you think about gases, gases are mostly empty space. Mostly empty space. So that means there's going to be a lot of space in between the particles of a gas. So that's why gases are going to be the most compressible. In fact, solids and liquids are rather incompressible, only compressible to a very small extent. Number 9, which of the following is not a unit for measuring pressure? Pascals is a unit for measuring pressure. So is torr. You might remember Evangelista Torricelli, who did the famous mercury experiment. So millimeters of mercury, that's also a unit of pressure, and so are atmospheres. The only one on here that is not a unit of pressure is kilojoules. Kilojoules are units of energy. Number 10 asks us to calculate the density of nitrogen gas at standard temperature and pressure in grams per liter. Well, we know the formula for density, which is density is equal to the mass over volume. But there's something interesting about standard temperature and pressure. And you might remember that the volume of 1 mole of a gas, so if I have 1 mole of an ideal gas at standard temperature and pressure, it has a volume of 22.4 liters. That's a volume that you have to have memorized. Now, where am I going to get the mass? Well, I know the molar mass of nitrogen, N2, is 28 grams per mole. And this volume, 22.4 liters, is for 1 mole. Therefore, my mass, I can just plug in 28.0 grams, and my volume is 22.4 liters. So when I plug that into my calculator, I get a density of 1.25 grams per liter, which is D. Number 11 asks us, what is the volume occupied by a mole of an ideal gas if the pressure is 626 millimeters of mercury and the temperature is 25 degrees Celsius? So in order to solve this one, we're going to need the ideal gas law, which is PV is equal to nRT. And we're looking for the volume. So we can rearrange the formula to be volume is equal to nRT divided by the pressure. We're given the pressure in millimeters of mercury. We're given the temperature. It's in degrees Celsius. And we're told how many moles we have. So we also know N. So N is equal to 1.0 moles in this case. And you could put as many sig figs as you want because it tells you it's a mole. So we can assume that's an exact number. So if we put in 1 mole, and again, we'll just assume that's an exact number. We multiply by the gas constant, 0.0821 liters atmospheres per mole Kelvin. And then we multiply that by the temperature. I've gone ahead and I've converted the temperature into Kelvin. And the way you do that is take 25 and you add 273 to it. So you get 298 Kelvin. And I've also gone ahead and I've converted the 626 millimeters of mercury into atmospheres. And the way that I did that was 626 millimeters of mercury. And I divide that by the conversion factor, which is 760 millimeters of mercury in 1 atmosphere. So I've already gone ahead and done that work for us. And that gives us 0.824 atmospheres. And you can see that my units all cancel out. So my atmospheres cancel, my temperature cancels, and the number of moles cancel, and I end up with a volume. So the volume that I get is 29.7 liters, which is C. Number 12, how can pure water be made to boil at a temperature below 100 degrees Celsius? Well, a boiling point is when the pressure exerted by the molecules in the liquid is equal to atmospheric pressure. So it's when vapor pressure is equal to atmospheric pressure. So if I think about, if I have some water in a pot, right, and I'm trying to boil that, okay, so I've got, a fire underneath there, and I'm trying to get those water molecules to escape into the atmosphere. So I have H2O liquid in here, and I'm trying to convert it into H2O gas. Well, how can I make that boil below 100 degrees Celsius? What I'm going to have is less atmospheric pressure. So if you think about what's holding those water molecules into the liquid phase, right, is there's going to be atmospheric pressure pushing down on them. So the less atmospheric pressure that I have, the easier it will be for the water molecules to escape into the gas phase. So because of that, I'm going to have to decrease the pressure below 1 atmosphere. So that would be A. And that is why in a place like Colorado Springs, where we're way above sea level, we have an atmospheric pressure that is below 1 atmosphere, and water boils at a temperature lower than 100 degrees Celsius. It's around 93 or 94 degrees Celsius in Colorado Springs. Question number 13. A sample of oxygen occupies a volume of 1.00 liters. If the temperature remains constant and the pressure on the oxygen is decreased to 1/3 its original pressure, what is the new volume? Well, hopefully you can see for this problem we are dealing with just pressure and volume, so we're going to need to use Boyles Law, which is P1 V1 is equal to P2 V2. They've already gone ahead and given us the original volume, which is 1.00 liters. Now I like to make things as easy as possible on myself, and it says that the the pressure has decreased to 1/3. So you have the pressure, and then it's decreased to 1/3 the original pressure. So we'll put the original pressure, I just chose arbitrarily 3 atmospheres, and then if I decrease that to 1/3, 1/3 of 3 is 1 atmosphere. So I'll put that over here, so 1 atmosphere. So now I'm going to solve for my volume, so for my V2, so V2 is going to be equal to P1 times V1 divided by P2. Now it's just a matter of plugging in our numbers. So we have our 3 atmospheres, and again we can assume unlimited significant figures there because I just chose that number arbitrarily, multiplied by 1 liter divided by 1 atmosphere. You can see that my units are going to cancel out, and I end up with my volume being 3.00 liters, which is A. Hydrogen cyanide is a poisonous gas that has been used to execute prisoners in the gas chamber. How many moles of hydrogen cyanide are present in a 67.0 liter cylinder at 25 degrees Celsius that is registering a pressure of 742 millimeters of mercury? So we're looking for the number of moles, and the variable that we use for that is N. We've already been given the volume, we've been given the temperature, and we're given the pressure. And we know the gas constant R, so thus we can use the ideal gas law, which is PV is equal to nRT, and we can just rearrange that and solve for N. So N is going to be equal to PV divided by RT. I've already gone ahead and done some of the conversions, so I converted the 742 millimeters of mercury into atmospheres by dividing by 760. So when I convert this, I get a pressure of 0.976 atmospheres, and I've also gone ahead and converted the temperature into Kelvin, which is equal to 298 Kelvin. So now if I just plug all of those numbers into my equation, I get my pressure of 0.976 atmospheres. I multiply by my volume, which is 67.0 liters. I have my gas constant memorized by now, 0.0821 liters atmospheres per mole Kelvin. And then I multiply that by the temperature. And let's check our units. So our temperature cancels out, as does our volume and our pressure, and we're left over with the number of moles. So when you punch that into your calculator, you get the number of moles is equal to 2.67 moles of hydrogen cyanide. So this is answer A. Question 15. Of the following gases, which will behave most like an ideal gas? So if you remember that the gas that's going to behave most like an ideal gas will be a nonpolar gas. So nonpolar. If we look at HF, we can see that there's a dipole in HF. Also in ammonia, if we look at the Lewis structure and then we draw the molecular geometry, you can see that there's a dipole, right? Because we have 3 dipoles going this way in the trigonal pyramid. So we have overall we have a dipole going this way. The next one, methyl chloride, that is also a polar molecule. So if I just draw it like this, you can see that there's a dipole going towards the chlorine. So that's a polar molecule. And then carbon monoxide, this is the Lewis structure for carbon monoxide, and obviously there's a dipole because oxygen is more polar than carbon. Whereas my nitrogen, if I draw the Lewis structure of nitrogen, there is no dipole, so non-polar. So N2 is going to be the answer. So we're just looking for which one of these molecules is non-polar. Moving on to 16. Which one of the following substances with their structures shown will not display hydrogen bonding? So you might remember that the requirements for hydrogen bonding, you either have to have a hydrogen bound to a fluorine, a hydrogen that's bound to an oxygen, or a hydrogen that's bound to a nitrogen. So we're looking for one of these bonds. So we are either looking for, again, we're looking for a nitrogen hydrogen bond, an oxygen hydrogen bond, or a fluorine hydrogen bond. Well, If I look in A, you can see I've got 3 nitrogen-hydrogen bonds, so that can have hydrogen bonding. Also HF, well, that's definitely got a hydrogen-fluorine bond in it. If you look at water, it's got 2 hydrogen-oxygen bonds. I'm just going to box one of them. And this next molecule, ethanol, also has an oxygen-hydrogen bond. Now, if you look at diethyl ether, there is an oxygen atom in the molecule, but there is no oxygen-hydrogen bond, so no OH bond. Therefore, there's going to be no hydrogen bonding with diethyl ether. Number 17, according to the kinetic molecular theory of gases, which statement concerning gases is true? Well, if you look at the first one, it says gases are mostly empty space. That's definitely true, right? The first one, the answer is A. So we think about gases, they're mostly empty space. The particles are very far apart, in a gas compared to a liquid or a solid. Let's just look at the other ones for fun. If you look at B, gas molecules are very closely packed together. That's not true whatsoever. C, gas molecules are strongly attracted to each other. No, gas molecules have elastic collisions, right? They just bounce off of each other. And the reason why is because they don't feel a strong attraction for each other. Also, another assumption that we made is, like I just said, is that the collisions of gas molecules with each other and the walls of the container are elastic. That means they don't lose energy. And it says here in D, when gas molecules collide, they lose energy. That's not true. They have elastic collisions. And then E, the average kinetic energy of the molecules increases with decreasing temperature. That's not true. The kinetic energy of the molecules actually increases with increasing temperature. So if the gas gets warmer, the molecules or atoms are going to move faster. So the answer is A. Number 18. It says we have a balloon at 25 degrees Celsius and it has 1.00 liters of air. The balloon is heated to 40 degrees Celsius at constant pressure. What is the new volume? So right now we're dealing with volume and temperature. So we see that the number of moles isn't changing, and we're also told that the pressure isn't changing, and thus we're going to have to apply Charles' law. Charles' law, which you need to have memorized. Charles' law is volume 1 over temperature 1 is equal to volume 2 over temperature 2. Now I've already gone ahead and converted these temperatures into Kelvin. So you have to convert the temperatures into Kelvin. I can't stress that enough. If you solve this problem using the temperatures in degrees Celsius, you will get the wrong answer. So originally, the first volume or the initial volume is 1.00 liters, and the temperature is 25 degrees Celsius. If I convert that into Kelvin, that's 298 Kelvin. Then the final temperature is 40 degrees Celsius. If you add 273 to that, you get 313 Kelvin. So now it's just a matter of rearranging my formula and solving for V2. So I'm going to do that down here. So I put V2 is equal to V1 times T2 divided by T1. Then I just plug in my numbers. So I have my 1 liter multiplied by my final temperature, which is 313 Kelvin, and then I divide by my initial temperature, 298 Kelvin. My units cancel out, and I get that my final volume is going to be equal to 1.05 liters. Question 19. What mass of helium is contained in a 2.0 liter balloon at 30 degrees Celsius and 735 millimeters of mercury? Well, to start off, let's write down what we know. We're given the volume, which is 2.0 liters. We're given a temperature, which is 30.0 degrees Celsius. 30 degrees Celsius in Kelvin, I just add 275 to it, and I get 273 to it, and I get 303 Kelvin for my temperature. And then for my pressure is equal to 735 millimeters of mercury. If I divide that by 760 millimeters of mercury per atmosphere, I can convert that into atmospheres, which is the units that I want for my calculations. I'm going to get 0.967 atmospheres. So we have volume, temperature, and pressure, and we're looking for mass. But if we know the number of moles of helium, right, if we can get the number of moles of helium, we can multiply that by the atomic mass of helium and figure out what the mass is. So let's start by using the ideal gas equation, which is PV is equal to nRT, and we'll rearrange that and solve for the number of moles of helium, which is going to be equal to PV divided by RT. So now let us plug in our numbers. So we get 0.967 atmospheres. My volume is 2.0 liters for my balloon. My gas constant is 0.0821 liters atmospheres per mole Kelvin. And my temperature is 303 Kelvin. You can see that the units cancel out. The units of pressure cancel, the units of volume cancel, and the units of temperature cancel, and we're left over with the number of moles. I'm going to move over here and write it down, and the number of moles of helium that I get is what? 0.0778 moles of helium. Now I'm going to multiply that by the atomic mass of helium, which is 4.00 grams of helium in 1 mole of helium, and I just got that from the periodic table. And you can see that the number of moles of helium are going to cancel out, and I end up with 0.31, something like 0.31. There's too many sig figs in the final answer, isn't there? Oh well, it's close enough. We definitely have the right answer, which is D, 0.31. They put an extra sig fig. There should only be 2 sig figs because there's only 2 sig figs in the volume. Number 20 says, which of the following is true for a liquid that is placed in a sealed container? All molecules stay in the liquid state. Well, that's not true because we know that when we place a liquid in a sealed container that we're going to get some evaporation of that liquid, and it's eventually going to reach an equilibrium. B, a set vapor pressure will be reached, which is the same at all temperatures. Well, that's not true because we know that as temperature increases, vapor pressure will increase. In C, evaporation of the liquid cannot occur. Well, that's not true. We're actually going to achieve an equilibrium between evaporation and condensation. D, condensation of the evaporated molecules in the jar can only occur once all of the liquid molecules are in the vapor or gaseous state. Well, that's not true. Could you imagine sealing off an Nalgene bottle with a little bit of water in it, and all of a sudden you turn around and it's all converted into a gas? Well, that's not going to happen. But if we take a look at E, it says once equilibrium is established between the liquid and the vapor, the rate of the evaporation process will equal the rate of the condensation. Now, we don't see that when we look at a sealed vessel, but we know that that is occurring. It's a dynamic process. So the rate of evaporation is going to equal the rate of condensation.